All right, I think we're probably doing pretty good at this point, so we can get started. So it's a pleasure today to be joined by Lachlan Lancaster, who to give our lunch talk today. Lachlan is a PhD student at Princeton right now, and his work is actually pretty diverse. I pulled up your publication list on ADS earlier today, and was reminded in particular of your paper on dynamical friction and fuzzy dark matter halos, which I really enjoyed reading. But today he's going to tell us about something completely different to that, and that is turbulent stellar winds. So take it away.
Yeah, thank you, Andrew. I'm glad to hear that somebody enjoyed the fuzzy dark matter dynamical. It was a fun project to work on. So yeah, thanks everyone for having me come speak. As Andrew said, I'm going to be talking about turbulent stellar winds, and particularly the winds from massive stars, O and B stars in particular. And I just wanted to mention that this is not just my work, but it's also the work of my collaborators, my thesis advisor, Eve Ostreicher, and Jungyu Kim and Chunglu Kim. All recently, until recently at Princeton, Jungyu is now in Korea at KASI. So to give you a brief outline of what I'm going to be talking about, I'm going to just go over some of the motivations for about why we care about O and B stars, and then and particularly their winds. Then I'm going to delve into sort of my work, how I've contributed to this, and our model for how to understand stellar winds. And finally, I'm going to come back to my recent work, most recent work, which should be on the archive next week. So we'll get to that at the end. So motivations. Star formation is the thing that we all care about, and in particular, the regulation of star formation. So this is a multi-scale process, sort of on the scales of galaxies. We have these galactic winds and outflows, which act to limit the amount of gas that lives within a disk that can collapse into a molecular cloud. And sort of within these molecular clouds, young stars are born. The most massive ones are very, very luminous and also have strong high velocity winds that act to disperse the clouds of gas, preventing it from collapsing into the protostars. And even on the individual scale of protostars, you have complex feedback processes interacting inflows and outflows and jets that determine the final mass of that star in a complex way. And these outflows also affect the surrounding gas and can affect the star formation efficiency on the overall cloud. But generally, when we talk about feedback on the scale of clouds, we think about the feedback from massive stars and how that can act to disperse clouds of gas. And as my title suggests, I'm most interested in the stellar winds that come from these massive stars. So why should we care about stellar winds in particular? So according to our sort of classical theory of how stellar winds affect their surroundings, this is due to, among other papers, this Weaver et al. 1977, they should dominate early feedback. And that the reason is that they can essentially build up so much energy that they can disperse clouds very, very efficiently. However, when we go and look at observations of stellar winds, and there's multiple ways to do this, but one of the best ways is by looking at X-ray observations of the hot gas. So these super high velocity winds shock and create super high temperature gas that you can observe in the X-rays. And when we look at those observations, in general, the X-ray pressures, sort of the energy contained within these X-ray bubbles is much lower than you might expect from this sort of classical solution. And so it appears that winds are doing less than we thought. And at the same time, when you go and look at all these, there's a number of great simulations that basically include stellar winds in their feedback prescriptions for understanding how stars form within molecular clouds. And generally, winds are important for a number of reasons, but it seems as though they don't have that much of an impact on the final star formation efficiencies. This is an ongoing theoretical exploration, but that's sort of a short summary of what has been going on. So the purposes of my work is sort of to say, what could be wrong? Why are winds so weak? So the basic idea, so what I'm outlining on the left here is sort of the classical Weaver model. And on the right here is what I'm outlining is sort of our change to that model. So we basically propose a new theoretical model of stellar winds now expanding into turbulent clouds, so not spherically symmetric. And to set the context here, we are ignoring the effects of radiative feedback. So it's just like the Weaver solution, it's just a wind expanding into a gas, not into anything that's been pre-photoionized or photoheated. And the classical stellar wind bubble evolution is spherically symmetric. You have this free stellar wind at the center, expanding from that adiabatically expands. That free wind goes through a strong shock. And this shocked stellar wind gets to extremely high temperatures. This is where the X-rays that I was talking about come from. And then you have a contact discontinuity because this is spherically symmetric. There's no way for things to move across this border. There's a contact discontinuity that comes between the wind and the swept up ISM. This shocked ISM shell is expanding at velocities much greater than the local sound speed. So you have a shocked ISM shell, and then finally the ambient ISM. And because there's no mixing at this interface, there's no way to remove energy efficiently from the wind interior to the bubble because it's extremely hot. It doesn't cool very efficiently. And what ends up happening is that the solution is energy driven, meaning that energy builds up linearly in time if you're assuming a constant luminosity wind, which for simplicity is what we're doing in this model. So what does our model do? The free wind is still quite the same. You still have a wind that goes through a strong shock, but now you're dealing with a turbulent background. And the basic proposal of our model is what happens if this turbulent background is so efficient at removing energy from the bubble from the wind bubble that your evolution, the evolution of the wind bubble, becomes momentum driven rather than energy driven. And what I mean by that is sort of the total radial momentum carried by the bubble increases linearly in time as opposed to the energy increasing it linearly in time. To what happens when you do that? I just want, before I talk about sort of the consequences of this, Mike, when these papers first came out, Mike Rudich tweeted this, and I really like this description of the old model as sort of the spherical cow and this new model as a fractal cow. And I'll get to sort of what I mean by a fractal cow instead. And I found a picture of a fractal cow, which is kind of nightmarish, but I thought it was cool and I should include it in this as well. So that's sort of the difference. So what happens when you include this? What's the difference between a momentum conserving and an energy conserving bubble? So the result is drastic differences. So here I'm showing a comparison between our solution, which is in the solid lines. I'm calling this efficiently cooled, our efficiently cooled solution, and the Weaver solution, which is shown in dashed lines. And what am I showing here? I'm showing the time it takes for the cloud to be for a cloud to be dispersed by stellar wind feedback for a cloud of mass 10 to the 5 solar masses as a function of the radius of that cloud, or equivalently its density. And the idea here is that you form some star cluster at the center of this cloud with some put in by hand star formation efficiency. So this is really just determining the mass of the central star cluster that's driving the wind expansion. And I go from 1% to 10% to really 100%. So the central cluster here is either 1,000, 10,000, or 100,000 solar masses. And what I'm showing here is the time it takes to disperse the cloud as a function of the cloud radius. The main takeaway here is that in our solution, in this efficiently cooled solution, it takes much, much longer for a cloud to be dispersed than it does in the Weaver solution. So the main takeaway, wind effects are much weaker than the Weaver evolution would have suggested. So here's sort of the same style of plot, but now I'm showing it to you in a number of different other quantities. So the plot I'm showing on the upper left here is exactly what I was just showing before, but now I'm showing the velocity of the shell being driven by this cloud. When it's turbulent, it will really have a range of velocities, but this is sort of, you can relate this velocity to the expansion of the bubble. And compared between the Weaver solution and our solution, velocities are much lower. Importantly, for what I was talking about before, so as I mentioned, we care about the pressure in the hot gas, and in particular, how that impacts the X-ray observations. And you can see what this is showing is basically the pressure in the hot gas at the cloud dispersal time. So these are all sort of as a function of the time at which this cloud is being dispersed, at the time that the bubble actually breaks out. And you can see the pressure in the hot gas in our solution is almost 2 orders of magnitude, in some cases lower than you would expect in the Weaver solution. You might say, that's crazy, that can't be consistent with with observations, but that is indeed the sort of reductions in pressure that we do see from X-ray observations. So this is great to see that if you just say it's momentum conserving rather than, or momentum driven rather than energy driven, you get this sort of correspondence. And finally here, what I'm showing is a very, back of the envelope calculation of what is the star formation efficiency needed to disperse the cloud, given if you had a Weaver solution or the sufficiently cooled solution. The main takeaway again being that if winds are efficiently cooled, you need a lot more stars in order to disperse the cloud than you would in the Weaver solution. So I've realized I've been talking a little bit fast. So please, if anyone has any questions, feel free to.
I was hoping, could you clarify what it means to disperse the cloud? Does it just mean it becomes equal to the background density, or?
Right. So in this these sort of theoretical back of the envelope calculations, I'm basically just saying we have some constant density cloud of some set radius, and I'm saying, imagine you have a source at the center that's driving a wind. The wind can either be energy driven or momentum driven. The dispersal is sort of when that bubble reaches the edge of the cloud. So this is a very sort of this part is a very semi-analytical sort of back of the envelope calculation.
And then the other question I had for the Weaver solution, sorry, I'm not a galaxy expert. As something expands, there's a lot of adiabatic cooling. So even if you're putting in a constant luminosity, I would think that it would also cool like 1/r.
Yes.
From the adiabatic cooling. So is that taken into account in those solutions? So
it does, but so the free wind is adiabatically cooling, but you're basically this is going at thousands of kilometers per second, right? And you gain up mass quickly, and so this outer shocked ISM can't travel that fast comparatively, and so you quite easily form a shock, and then this shocked volume actually ends up taking up most of the volume of the bubble, and that's not adiabatically cooling, expanding. It's mostly thermal energy.
Okay. Okay. Thank you.
Yeah. Cool. Any other questions? Okay. So I'm going to come back to some of the theory that is, so that, as I was saying, is sort of just some back of the envelope calculations of what the consequences of being momentum driven rather than energy driven are. But before and I'm going to come back to some of the math of why that makes sense, why that might make sense. But before I do that, I thought I would first talk about sort of give you some pretty pictures. And so the first paper, which I'm going to come back to, is all of that theory and some observational comparison. And in the second paper, what we do is run a large suite of 3D hydrodynamical simulations to sort of validate the theory. So here I'm showing, there's a lot going on here, but here I'm showing a slice through one of our simulations run at high resolution for parameters which are meant to represent something like a superstar cluster. So the gas here is 10 to the 5 solar masses of gas contained within 5 parsecs. The diameter or sort of the length of this box is 5 parsecs. The panels are showing density, pressure. This is the cooling time of the gas versus the pressure. Momentum being carried by the bubble. You're seeing that most of the momentum is being carried in the shell. This is the temperature slice. In the normal Weaver solution, this very, very hot gas would be the shocked gas, but as you can see, it's not this spherical structure, and there's the adiabatic wind is actually taking up a lot more of the volume. This is your typical temperature density phase diagram. This is showing the fraction of gas that is in wind, and then this is showing the cooling density. The bottom right here is cooling weighted temperature histogram. So where is most of the cooling going on as a function of temperature? So there's a lot going on here, but I just want to point out a few things worth noting. There's a very, very complicated interface between the bubble, the hot bubble, and the cold gas in the background. And as I'll come to, this can be described by a fractal, but it's particularly evident in the temperature. So sort of the intermediate temperatures here, which you can see as sort of this off-white, and also in the cooling. At the same time, we're also capturing a lot of the mixing. So this is tracking the wind material, and you can see there's a lot of mixing that comes in. Finally, we also, part of our model is that most of the cooling is going on at basically one temperature, and that is borne out in the simulations. So basically the peak of cooling happens at this sort of 10,000 Kelvin where cooling can occur very efficiently. So you can see that these bubbles are a total mess, but it turns out that we can still describe their properties quite efficiently. So what I'm showing here is basically the volume equivalent radius, so defined as the radius of the sphere with the same volume as the volume occupied by hot gas in our simulations. And what I'm showing is this equivalent radius for the expansion of a bubble put at the center of this turbulent medium, and how that radius expands in time for different cluster masses. So it's basically these different colors are basically determining the luminosity of the wind that's driving this bubble. And the black lines here are basically the theoretical expectation that you would put down for something being a momentum conserving solution. So the P dot W here is basically the momentum, direct momentum input by the wind, which is just the wind mass loss rate times the wind velocity. And as you can see, the different line styles here are showing different resolutions. So we moderate increase in the bubble radius as you go to higher resolution. But in general, it very, very well follows the scaling that you would expect for the momentum conserving solution, and is well resolved. So that's awesome. Even though you have these total messes, it still follows a theoretical prediction like you might expect. And you see the sort of more important parameter is the momentum, because I'm arguing that this is a momentum conserving solution, or a momentum driven solution, meaning that the radial momentum of gas carried by the bubble increases just by the momentum of the wind that you put in. And these black lines are showing that for these different luminosities of wind sources. And you can see that it's very, very closely follows the evolution that you would expect. Something to note is that generally when you go to lower luminosity winds, you do have some moderate enhancement above what you would expect for the momentum driven solution by itself. And I'm not going to have time to talk about it in too much depth, but we do in an appendix go into explaining where this extra enhancement comes from and how it's related to turbulence. Any other questions there? Cool. So to set you up for some of the math that I alluded to earlier, I thought I'd show a pretty video of how these simulation bubbles evolve first. So what I'm showing here this is something more like a typical GMC. So this is the center here this is basically gas density that's something like a 10 to the 5 solar mass cloud with a 20 parsec radius. So that's this box is 40 parsecs on the side. And I basically put in by hand a 1000 solar mass star cluster particle and the wind that's driven by that. And here I'm showing the evolution, a slice through the center of the simulation and evolution in density, pressure, the cooling density, and the fraction of the gas that is in wind material. So as we can see, as I said before, there's a very complicated interface here. Even though that's the case, you can see that most of the cooling is going on at that complicated interface. As opposed to the other snapshot I was showing you, where there was a very, very oblique shock surface in this lower star formation efficiency simulation, you have a little bit more, a less oblique shock surface. And as I sort of alluded to before, that's related to why there's a little bit of an enhancement above purely momentum conserving. At the same time, we're tracking all of this interesting mixing of the wind material into the background gas. So with that pretty movie out of the way, I want to sort of delve into how we can explain some parts of this theory. So how can we explain or measure whether or not it's feasible for these winds to be cooling so efficiently? You're removing almost 99.9% of the wind energy, it turns out. So how can you do this? So one way to think about this is, well, can I just compare the energy flux that's being provided to this interface by the wind to sort of a energy flux that I think that this surface has the capacity to cool away? So that's what this phi cool is. And the general idea is the capacity for the wind to cool away material greater than the capacity for the wind to provide provide energy to the interface. So we can measure this pretty straightforwardly. Basically, the energy flux of the wind that's being provided to the surface is basically the hot gas enthalpy, the enthalpy of the gas in this hot shocked wind, times the post-shock velocity of the wind, which if you're going through a strong shock, it's sort of a quarter of the wind velocity, but there is some deceleration over the shocked wind area. So you have to account for that, and I'll come back to that. But how do you sort of think of this phi cool? Well, naively, you can imagine that, and there's a lot of this work is sort of based on some interesting similar work that's been done in the CGM community when it comes to cloud crushing and galactic winds and turbulent mixing there. But the idea that's come out of that work is sort of that you can think of the enthalpy as being basically the quantity that's related to the energy, and the thing that matters is sort of what is the velocity, the equivalent velocity that you're able to mix things in. So I'm basically transforming this from a comparison of energy fluxes to a comparison. I'm assuming that the pressure is sort of the same on either side of this equation, and then trying to compare the velocity, the post-shock velocity of the gas to some equivalent mixing velocity from cooling. So how do we try and think about that? So like I said, we're trying to seek a characteristic velocity for the absorbing of hot gas energy. So because it's turbulently mediated, we think that this velocity is basically going to depend on the scale of turbulence in the hot gas. So what I'm showing here is sort of an overlay of on the schematic diagram is the turbulent velocity field, the magnitude of the turbulent velocity field in the hot gas, and you can see that it's quite structured. So what we want to end up measuring is sort of what is the scale of that turbulence. And the idea here is that you have some turbulent cascade, you have turbulent velocities on larger scales that then when they encounter this surface, mix and cascade to smaller scales. And eventually the scale that matters is the cooling length scale. So that's the scale on which your cooling time is comparable to your eddy turnover time. And that's sort of where all of the actual energy is going to be lost. So these two terms are basically accounting for that cascade and setting that scale based on the cooling time. So this is the outer velocity scale, which you can measure in the simulations, and you need something to account for how that cascade happens, and that depends on sort of the structure function of the velocity, and it turns out also sort of some parts of the fractal structure. And that's basically what this term is saying, and what that ends up being is an enhancement on this velocity. So finally, I said that you have this turbulent cascade from larger scales to smaller scales, and the only scale that matters in terms of the cooling is this small scale cooling length, because that's where all of the actual energy is being lost. But the larger scale turbulent cascade sets up a fractal interface between the interior of the wind bubble and the background. So you can imagine if instead of this complicated interface, you just had a sphere with a bunch of little eddies turning over on the cooling length, that wouldn't remove nearly as much energy as if you have cooling length eddies sort of happening all over this large fractal surface that's been instantiated by sort of the larger scale turbulent cascade. And basically what this last term is doing is accounting for that enhancement that you get. And what I'm showing here is the effective bubble radius that I mentioned before. This is again L, the scale on which you're measuring the outer part of the turbulence. And this D here is the what we call the excess fractal dimension, which is again something that you can measure in our simulations. So the idea of this exercise is basically we can measure this in our simulations, the velocity structure in the hot gas, and we can measure the fractal dimension of this interface, and basically, can we make these things match one another? Does this inequality, this comparison make sense? So again, to give you an idea of how we measure the excess fractal dimension of these surfaces, this is from some similar mixing length theory, or sorry, turbulent mixing layer theory work that came out last year by Drum and Fielding. And if you remember from if you were as much of a math nerd as I was and was obsessed with fractals, then you may remember some sort of box counting algorithms, or read about how you can measure the coastline of England with larger and larger rulers or smaller and smaller rulers, and how that changes your answer. So that's basically what this excess fractal dimension is. We basically define some surface. So in our simulations, that's an isotemperature surface around where we expect the cooling to be going on. And we measure that surface on different scales. So you can imagine going from this larger scale, very coarse understanding of this surface, down to finer and finer scales. And you measure the surface area of that surface at each of those scales. The excess fractal dimension is essentially the logarithmic derivative of that area that as a function of scale with respect to the scale on which you're measuring the area. Cool. And the basic idea, we can do that in our simulations. There are some trends with the different simulations in terms of what kind of wind you're investigating and how that affects how that changes the fractal shape of the cloud, of the wind bubble, and some dependence on sort of the cloud sizes and moderate dependence on sort of what temperature you're using to track this isotemperature surface. But in general, this excess fractal dimension D of 1/2 is about right. So from going on from now, I'm just going to accept a D equals 1/2. Also worth noting, so this is shown, these are over all of our different simulations, so from sort of 1% to 100% star formation efficiency. And I'm showing sort of that this derivative as a function of the scale on which it's measured down to the resolution scale. When you get to the resolution scale of a simulation, you can't form any smaller scale structure. So this fractal dimension you would expect has to go to 0. And indeed it does. But what I'm looking for is sort of the larger scale here, and that is about 1/2 as a good number. Okay. Any questions there? Cool. So I said we can measure the. Yep.
Can I ask a question about this? So does this depend at all, like the fractal dimension, on the makeup of the gas, like the, I don't know, the dust content or the metallicity overall?
So yeah, I'll say in terms of my simulations, I'm completely ignoring dust. And that the interaction of, I'm very interested in understanding sort of the interaction of dust with these mixing layers in the future, but I haven't done that. I'm trying to think of how, I think the main thing that could easily affect this excess fractal dimension is sort of the structure of the turbulence and how much structure you've put into that turbulence. So we've sort of accepted, we've put in things that we think is reasonable for a turbulent molecular cloud, but there are other reasonable things that you could put into the background in terms of what is the density structure. I think that would be the first thing to change something like this.
And how much is that turbulent structure is supposed to vary, like in different environments, like even like across the disk of the Milky Way or in lower mass systems?
Yeah, so we basically put in, you can, it depends. The basic idea is that you can put in a reasonable expectation for what the structure, what the scale dependence of the velocity will be. That's relatively well theoretically understood. So that's relatively theoretically understood, and you can put in, and I put in something for what the velocity is going to be as a function of scale. That is sort of energy conservation physics, so it doesn't really change, it shouldn't change too much from environment to environment. And what you would, I would say the important thing for this sort of simulation is that there's structure at all in the background. The exact degree of structure, I think, is something that's worth investigating. We sort of just chose what would be reasonable amounts of structure, and saw that indeed these winds are efficiently cooled. But you can imagine that as you move towards a more uniform background, eventually you need to sort of recover the Weaver solution. So what is the exact amount of structure you need in the background for this to occur. And I haven't, it's something I've thought about, but I haven't investigated really yet.
Yeah, that's
I guess a
interesting.
different way the length could differ with velocity scale, or scale, the velocity could differ with length scale is like if you had a magnetic turbulent regions versus more pure hydrodynamic turbulence, right?
Yes, that is definitely true. And that is sort of, that is, I think, for that is sort of, so with the general question of sort of having any sort of background and seeing how you transition from the Weaver to something like this, that's just a large parameter space, and it seems like not super physical. There's no good physical motivation, but the first next thing to do, I think, is include magnetic fields, and that's much more realistic and physically motivated. I have started doing those simulations, but I don't have any results to show, unfortunately. But you're right that does qualitatively and quantitatively change the structure of the background. Did you have any other follow-up, Anna, or?
No, that's great, thanks.
Okay. Cool. So as I said, we can measure this fractal dimension, and then we can also go and measure the turbulence in the hot gas. What I'm showing here is basically the structure function of the turbulent velocity fields in the hot gas. What's interesting is so again, a similar color scheme, but I'll go over what I'm showing again. This is a 20 parsec cloud, 10 parsec, 5 parsec, 2.5 parsec. All of the parameters are sort of chosen to represent a 10 to the 5 solar mass gas cloud at those scales. And each of the star particles are put in by hand at the center with a star cluster mass of either 1% of the cloud mass, 10%, or 100%. So even though the basic luminosity of the cloud is varying by an order of magnitude between these simulations, the velocity scale is maybe varying within a factor of 2, if even. So that's interesting to note. And basically what we care about is the velocity scale at this sort of outer energy containing scale, and how that goes down to the cascade. What I'm showing in black here is sort of the turbulent structure function with an amplification to put it on the same scale as all of these other things, but the turbulent structure function of the background before we started any of the winds. And you can just note that they're quite similar across these different simulations, and that probably has an impact on the structure of these, though again, we haven't investigated that in depth. Cool. So I've measured the things that I said that I needed to measure in order to get a handle on this sort of effective velocity for mixing wind out of the hot bubble. And I also mentioned, in order to compare that to the post-shock velocity, I also needed to account for how the post-shock gas is decelerated over this region. So there's a prescription in our paper for doing that, but then we can basically compare these things to one another. So the solid line I'm showing here is basically that effective mixing velocity, and the dashed line here I'm showing is the post-shock velocity. In our simulations, this is for the 20 parsec cloud simulations. And the interesting thing here is that they track one another very, very well. So it is reasonable to expect and see that that these bubbles are actually cooling as efficiently as we might expect them to be, in order for them to be momentum driven rather than energy driven. So the picture holds together. So just to give you some main takeaways before I go into some of the more recent work, basically the turbulent cooling losses can help us to understand the low X-ray luminosities that we see in wind bubbles in the local universe. This can give much better agreement with cloud lifetimes when you're thinking about sort of observational constraints on the lifetimes of clouds from observations of nearby galaxies, this gives a much better agreement than you would infer from the Weaver solution. But winds, I don't want the main takeaway to be, especially because I've worked on winds so much, I don't want anyone to be thinking that winds are unimportant. They can still be dominant at early times and be very important in high density gas. Okay, any questions there before I move on to some more recent stuff? Okay. So in a paper that should be on the archive next week, we investigate the even more realistic scenario of self-gravitating, self-consistently star-forming gaseous cloud and simulate how such clouds are dispersed by feedback just from stellar winds. So here I'm showing one such cloud with a radius of 20 parsecs and a total initial mass of 10 to the 5 solar masses that is initially initiated with some turbulent velocity field. Let's see. On the left, I'm showing the gas surface density, and you can see that that collapses to form individual stars. On the right, I'm showing the X-ray intensity, and that's basically a tracer of the hot gas from these winds. And you can see how the cloud is basically completely dispersed by the stellar wind feedback. So now we have this more realistic scenario, and the question here is to basically ask, is it still true that a lot of the energy is being lost to turbulent cooling as we had sort of proposed before? So even before this, there had been sort of this picture people had thought going back to the early 2000s of how to remove, so before even Harper, Clark, and Murray, of how to explain these low luminosities seen in X-ray bubbles. And there was sort of these two pictures. One way to remove energy is to allow it to escape efficiently. So if you imagine you're blowing a bubble and you put a needle in that bubble, it's very hard to keep blowing the bubble. So what that is called or referred to here is essentially leakage. And the idea is that, or bulk advection of the wind gas out of the cloud. And the idea being that you have stars forming in a cloud and expanding into winds, but the cloud is very porous and some of the winds just escape. So that was sort of initially written down and explained by this paper, Harper, Clark, and Murray in 2009. And then on the other hand, you have energy being efficiently removed by this turbulent mixing with cooling that was talked about in Anna Rosen's 2014 paper, and that we sort of expanded on and given a model to here. So which of these two scenarios is sort of dominant? Is it true that cooling is still extremely important, or does the bulk advection play a role? So we can investigate that within these new simulations, and the answer is yes, they're both important. So what I'm showing here is essentially as a function of time, where is the luminosity of the wind going? So this is throughout the simulation. This blue line is showing the fraction of the wind luminosity that's going into cooling. The red is showing the fraction of the wind luminosity that's being advected out of the domain. And this sort of teal cyan line is showing the fraction that remains. So again, we see that only up to 1% of the energy is remaining within the cloud, and that's including kinetic and thermal energy. So both the thermal energy in the hot gas and the kinetic energy of the swept up medium. But as you can see over the time scales, basically you have both cooling and leakage, but cooling is dominant at early times, whereas leakage tends to dominate at later times once the cloud starts to be dispersed thoroughly. And we call the transition between these as sort of the breakout time, as when you transition from being a cooling dominated losses to leakage dominated losses. And that you can think of as sort of when in all of these simulations, you actually see the cloud breaking apart more easily. So Also, now that we've run these simulations, we can use them to test star formation efficiency theories that basically say you have some turbulent structure within a cloud, you have some constant momentum input rate by some sources, and compare how those basically compare Eddington ratios and see how much things are moved out of the cloud and how that determines the star formation efficiency. So that's basically what these two papers, these theories that I'm referencing here do, and we can compare that against our simulations and see pretty good agreement that the star formation efficiencies you might expect for a constant momentum input rate feedback mechanism are well behaved. So this sort of the assumption of computing these lines and comparing them to our simulations is that winds are momentum driven rather than energy driven. And the fact that there is a good comparison between these two things is sort of reassuring in our picture. Indeed, it sort of has to be because you can see that so much of the energy is being removed here. So you would naturally expect, because there's so much energy being removed, the wind would be momentum driven rather than energy driven. So we have the star formation efficiencies checking out as well. And then finally, with these simulations, we can also track what fraction of wind material finds its way back into newly formed stars. So I'm calling this quote unquote self-enrichment. I put this very much in quotes because these simulations are from winds of O and B stars that we are studying, and that we're studying here, and they have essentially the same chemical composition as the gas from which they formed. But it's still interesting to see how does wind come from a massive star, start out very, very hot, and find its way back into subsequently formed stellar populations. So what I'm showing here is basically the fraction of mass in wind as a function of the total stellar mass formed within our simulations divided by the final stellar mass. So again, this is a proxy for time evolution here. The solid lines are showing the average over all of the gas in the simulation. The dashed lines are showing the average of all stars that are being formed in the simulations. So these are sort of stellar particles. And the points here are showing individual star particles within the simulation. Interesting things to note. You can notice that the star particles, the enriched star particles, or star particles with wind gas in them, are considerably above both of these. And that's because the enriched ones are forming where there's a lot of wind gas, and that mixing is not, at least in terms of a global scale, is not as efficient. So what's not being shown here is all of the star particles that are sitting at minus infinity on this log plot because they have no wind material, but those stars are playing into the dashed line here. So that's why you have star particles above sort of the average of the star particles, and you're not seeing the ones that are below. But generally, you can also see that there's a relatively nice power law-ish dependence of F wind on M star. And that basically just comes from the fact that the luminosity, the mass loss rates of these winds are relatively constant, and the star formation essentially follows, for the beginning of the simulation, it follows a linear star formation history graph. So those two things together gives you sort of this nice line in the log plot. But so you can easily explain that, but nothing super crazy going on there. So the hope is that with future simulations of winds that are chemically enriched, we can hope to answer how real self-enrichment can act within these star-forming cloud simulations. So to conclude and summarize this more recent work, both, it turns out when you're considering energy losses from winds, both cooling and leakage are important in these more realistic simulations for removing energy, but cooling tends to be dominant at early times, and it turns out most of the timescales over which star formation occurs. So cooling seems to be the dominant mechanism in terms of caring about how energy is lost over the star formation period. When we use constant momentum input rate predictions to predict the star formation efficiency, those match our simulations quite well. That's a good self-consistency check. And finally, we've given sort of a first understanding of quote unquote self-enrichment in these sorts of simulations, but there's much more to be done to connect back to real chemical enrichment and understanding how chemicals are moved throughout the galaxy. So thanks, I'll end there and ask if there are questions.
Great, thank you, Lachlan. We have time for questions. If people have them, I see Mike has his hand raised already, so.
Hey, great talk. Thanks a lot.
Thanks.
Sorry if you already showed this. You may have. What temperature of gas is doing most of the cooling?
Yeah, so I kind of showed it, but it was in this multi-panel plot. So what I'm showing in the bottom right here is the cooling weighted temperature histogram. And basically most of the cooling is happening around 10 to the 4, or it's really a little bit below 10 to the 4 is the peak of the cooling curve. So it's mostly Lyman alpha.
Okay, so the second part was, I was wondering how different this would look at low metallicity.
Right.
And I guess if it's Lyman alpha, then you would guess not so different.
Yes, that's the idea. Of course, you can see that there is some significant fraction of cooling that is happening at these higher temperatures, and that could change. But we do see that, at least in these, these are all assuming solar metallicity, and there, because most of the cooling is coming from Lyman alpha, you would imagine that it doesn't change that much with lower metallicity. Of course, winds themselves do become much weaker at lower metallicity, at least these kinds of winds.
For, I guess, normal stars, but people also talk about how maybe you can get weird, very massive stars in low metallicity conditions. So that's why I was asking, but yeah, cool, thanks.
Mm-hmm.
Do we have any other questions? I had one I wanted to ask about the fractal dimension of the surfaces that you were showing. Is that in any way, so you're measuring that directly right now, is that in any way sort of derivable from some understanding of turbulence?
Yes, and it's been on my to-do list to think about that. I think but I'm sure that Drummond has thought about it a little bit. I think so. You get these sort of fractal dimensions in sort of if you think about like a Koch snowflake, one of the fun, or a Koch curve, basically just understanding how much you're adding every time you go down a step, right? And so you could think very reasonably, like, if these fractal dimensions are coming, so in this, the problem I'm showing here, this is just a Kelvin-Helmholtz instability. And you can imagine that you could very easily define or come up with what the fractal dimension should be in that problem based on the scaling. Drummond's approach, at least in this paper, was to basically just run the simulations and measure the fractal dimension and saw that it is 1/2. In simulations more like mine, where you have a bunch of different interacting instabilities and a lot of other structure, it might be harder to say, give a theoretical prediction of what exactly the fractal dimension should be. But You could. I can imagine thinking about doing that, but I haven't gone into depth thinking about it. So
Great, thanks. Anna, you have a question?
Yes. Yeah, I was wondering about the timescales you are inferring for the dispersal of the cloud, and if the like those numbers can be interpreted in terms of or what are the implications for formation of globular clusters. And I guess this really ties back because we talked about it earlier, whether this can help like understand how the anomalous chemical abundances came to be.
Mm-hmm. So that is my one of the long-term things that I'm interested in. I think in terms of timescales, when you're talking about timescales in normal star forming GMCs, you need to and sort of what timescale that happens over. Winds aren't the only important feedback mechanism, and to get right timescales there, you need to include all of the different feedback mechanisms like Mike's simulations do, for example. So it's not as good to make a comparison there. At the same time, when you go, there's a lot of uncertainties as you go to higher redshift. But when you're considering denser and denser star formation, in general, sort of some of the radiative feedback effects become comparably less important. And winds can play more of a role in determining what the lifetimes are there. Sorry, did you have a?
No. Yeah,
okay.
I'm trying to follow. Yeah, what you're saying. Yeah.
Yeah.
Okay, that makes sense.
So there generally the timescales are. I mean, in the very dense simulations, you're thinking of fractions of a mega year. Or even 1 mega year, 2 mega years. And how that relates back to multiple population and chemical enrichment in globular clusters comes down to what is the weird thing that is doing the chemical enrichment, and over what timescales is that able to put mass into the surroundings. If things act the way that we think that they should, that timescale has to be quite short. And I think putting interesting constraints on sort of what that timescale has to be will be interesting for at least giving one sort of constraint on the globular cluster formation scenario.
Right. Thanks.
All right, any last questions? Don't see any more. So in that case, let's thank Lachlan again for a really nice talk, and thanks everyone else for joining us.
Thanks, everybody. Bye.
Thank you. It's really nice, really interesting results.
Thanks. Okay. Bye, guys.